All right, so let's look at this third example together. And this gets into the more typical problems you'll see. So if water runs into a cone-shaped tank at a rate of 9 cubic feet per minute. Now, I want to stop right here and mention that 9 cubic feet per minute is a rate. So do you recognize, because it's cubic feet, that's measuring volume, so that must be the rate at which volume changes with respect to time. And in math language, that's dV/dt. So now I can say 9 cubic feet per minute. All right, so let me keep reading the problem. The tank stands point down and has a height of 10 feet, a base radius of 5 feet. Okay, now this is important. I'm not going to write it down, but we're going to come back to it. The fact that it has a height of 10 feet and a base radius of 5 feet tells you that the height is double the radius, or the radius is half of the height. And that is regardless of how tall the water is in the tank. So if the water is all the way up to the top of the tank, then the radius is going to be half the height. If the water has dribbled out and is just at the very, very bottom tip of the tank, then the radius is still half of the height of that water at that point. So keep that in mind for later. How fast is the water level rising when the water is 6 feet deep? So do you see where it says, how fast is the water level rising? Now, that it's asking how fast is the height of the water rising? So the rate at which h is changing with respect to time. So that would be dh dt, and that's the big question in the problem. So now I know I basically need an equation that has something to do with volume and height, okay? So when it says when the water is 6 feet deep, this is your time-specific question. That's your time-specific information. So remember, anything that's time-specific, you do not insert until after you take the derivatives, okay? So I can't put that in at first because if the water's flowing into the tank, the height of the water level is changing with respect to time, which means the radius of the circular surface of the water is also changing with respect to time. All right, so I'm going to start out with what I know, and that is that the volume of a cone is a third of the volume of a cylinder, and the volume of a cylinder is the area of its base, which is pi r squared, times height. So let me say that again. The volume of a cone is 1/3 the volume of a cylinder. The volume of the cylinder is the area of the base, which is a circle, times the height. Now, our issue is that we have R and H in this problem that are both variables. Well, if you look at our purple and blue information, we want V in the problem so that when we differentiate, we get a dV/dt term. We want H in the problem so that when we differentiate, we get a dH/dt term. We do not want R in the problem because if we have the R in the problem, it's going to force us to do product rule when we take derivatives, and it's going to cause us to need a dr/dt term. Well, I don't have dr/dt. I could find it. That's a harder way to do this problem. So instead, let me rewrite the equation we have in the most user-friendly manner that we can. So what I want to do is take r squared and replace it in terms of h. So remember what I said about the orange information? The radius is, if the water in the tank is all the way to the tip top, so if the tank's full, the radius is 5 feet, and the height of the tank is 10 feet. Well, that means the radius is always half the height. So, like for instance, if I drew on this picture, then I would have a radius of that triangle and a height of that triangle. And that radius and height will always be similar to the radius and height of a full tank's triangle, so to speak. So I know that the ratio of 5 to 10, which is a half, is always going to be the same thing. Anyway, if the radius is half the height, then I'm going to put half the height right there in my equation. So now I can rewrite my equation in the most derivative-ready form, so just like when we did optimization problems. So I'm going to spend a minute getting things cleaned up. So I'm going to have 1/2 h quantity squared is 1/4 h squared times my outside h. So I'm not doing anything with derivatives until I clean up. Let me make all my numbers in the problem pi over 12. And then my variable portion will be h cubed. Now see, remember, my purple and blue information tell me I need to work with dv/dt and dh/dt only. Well, now I can do that because my equation has only v's and h's. All right, so here I go. Take the derivative of both sides. So the derivative of v with respect to t. Now on the right-hand side, my derivative would be 3 times pi over 12 h squared, and then I have to say, oh yeah, times the derivative of h with respect to t. Now, of course, that 3 pi over 12 can be replaced as pi over 4. So I've got dv dt, and I could really do this step and the next one as 1, but I'm going to say that's pi over 4 h squared dh dt. Now let me start inserting what I know. So I know that dv dt is 9, so I'm going to insert that right there. And then I've got pi over 4. I also know that it wants what's going on when h is specifically 6. So I can insert 6 squared right there. And then finally, what I want is dh dt. So my job is now to algebraically isolate dh dt. Let me do a little cleanup work. So I've got 9 equals pi over 4 times 36 times dh dt. I've got 9 equals. Well, notice 36 pi over 4 reduces to 9 pi dh dt. And now I could say that dh dt equals 9 over 9 pi, which is 1 over pi. Now, if the volume was measured in cubic feet, then height is just measured in feet. Of course, you can see that on the picture labeled in pink anyway. But that would be, uh-oh, that was my board doing weird stuff, feet per, and I believe it's minute, is it not? Yes. All right, so let's go to the next problem and see how we do. A 13-foot ladder is leaning against a house. Now, I want to mention something about this. The 13-foot ladder is a measurement that will not change over time. Even as time passes, the ladder is going to stay 13 feet. Because that measurement is not time specific, you may plug that quantity into the equation before doing the derivative. All right, its base starts to slide away from the house and is sliding at a rate of 5 feet per second. Okay, so let me mention this 5 feet per second. If that's the rate at which the base of the ladder is sliding away from the wall, what you're measuring is the change in x, which if you look at the diagram I've given you, is the measurement from the base of the ladder to the wall. So I'm going to say that dx dt is 5. Now, something else we need to think about is whether our rates are positive or negative. So I'm going to say, because that would push the x going in the rightward direction according to the way I've labeled the picture, then that would be positive. If x were shrinking, then I might say x, the dx dt part's negative. You'll see that in other problems. All right, so it says when the ladder is 12 feet from the house. So when the ladder is 12 feet from the house, that's time specific. So I'm going to say we've got a time specific quantity, which is x equals 12. That's going to be important. Remember, you cannot put time specific values in an equation before you take the derivative. At what rate is the ladder sliding down the wall? Now, at what rate is the ladder sliding down the wall? That tells you in part A. Your question is, what is dy dt? So y should be shrinking because the ladder's sliding down the wall. So I'm not going to be surprised if I get a negative value for y later on. Let's just deal with part A right now, okay? So the first thing I notice, if I need an equation that has a dy dt and a dx dt in it, I need to start with an equation that has an x and a y. So do you recognize that, number one, when I look at the picture, that theta doesn't seem to have anything to do with part A? And the equation I need to work with is just the Pythagorean theorem. And like I mentioned earlier, I can go ahead and put in 13 squared because the length of the ladder is not changing over time. So that number can be inserted from the get-go before derivatives. Okay? So now I'm going to be able to differentiate and get a dx dt and a dy dt term in the differentiation with no other weird terms in there. So I'm going to have 2x dx dt plus 2y dy dt equals the derivative of 169, which is 0. So that's gone. That's going to make things easier. Now, right now, I can begin to plug in some values. So I see that, for instance, I can say 2. It says when x is 12, so that's a time-specific measurement. Dx dt is 5. I can plug that in. But now I get a bit of a issue because I don't know what y is. So I'm just going to hold on to that for a minute. And then dy dt is what I want, so I can go ahead and plug that in. And then that's all equal to 0. So I've got to do something to figure out y if I'm going to solve for dy dt. That blue variable is the only variable I can have. Everything else needs to be numbers. Okay, so sometimes you have to take steps to draw a time-specific picture. So on my time-specific picture, when specifically x is 12, the ladder's always 13. Oh, I can see at that point in time when the ladder is 12 feet from the wall, the ladder must be 5 feet up the wall because I've got a 5, 12, 13 right triangle. Oh, so sometimes they'll give you time-specific information about one variable, and you can use it to figure out time-specific information about another variable. So guys, I am ready to rock and roll. I can solve for dy dt now. That's awesome. So let's see here. I have 2 times 12 times 5. So 12 times 10 is 120. You can also divide out the 2's, by the way. Plus 2 times 5 dy dt equals 0. So dy dt equals, do you see that I would subtract 120 and divide by 10? And that's going to be negative 12. So that makes sense again, because since the ladder is sliding down the wall as the base of it slides away from the wall, it makes sense that the y is dropping and the rate would be negative. I hope that makes sense to you. So dy dt is going to be negative 12. And again, it's going to be feet per second. So again, that just says that the ladder is sliding downward at a rate of 12 feet per second. So that's what the negative is, the downward part. All right, so let's look at part B. On part B, at what rate is the angle between the ladder and the wall changing at that moment? Okay, so this one, at what rate is the angle between the ladder changing? All right, that is asking you what is, if you look at the way I've got the picture labeled, that's asking you for d theta dt. Okay, now listen. I have dx dt, I have dy dt, I want d theta dt. So I needed an equation with either x and theta or y and theta. And that's it. I don't want any other weird letters that I wind up with something else going on. Well, if I just look and say, well, let me just use theta and x, what I can do is say, well, let's use basic right triangle trig. So could I say that sine of theta equals x opposite over 13 hypotenuse? Now, guys, you could also say that cosine theta is y over 13. I think I would prefer not to do tangent theta equals x over y, because then I would have two variables, which would require me to have d theta or dx dt and dy dt in the same problem. And then I also wind up getting into needing to use quotient rule when I do derivatives. So do sine or cosine. All right, so I'm going to do the same thing. The derivative of sine theta is cosine theta. Oh, times d theta dt. Look at the right-hand side as 1/13 x. Don't use quotient rule. 1/13 times x. The derivative is 1/13 times the derivative of x with respect to time. So again, I need to figure out what cosine theta is and d theta dt. D theta dt, keep in mind, that is my unknown. All right, the 1/13, and I've got to come back and I'll figure out cosine theta in a minute. Dx dt, you already know, is 5. So I can plug in some of this information from the previous problems. So the issue is, what do I do with this cosine theta? Well, remember, go back to your time-specific picture. At this point in time, no, sorry, that's my screen doing weird things. If I, there it goes again. My bad. Theta's right here. At that very point in time, cosine theta is 5/13. So notice I don't have to find theta. I need to find cosine theta, which makes this problem a whole lot easier. So I keep using the one bit of time-specific information I've got to find the other things that I need at that specific point in time. So I'm sure that you all can see that d theta dt is going to be 5/13. That's the 1/13 times 5 on the right. And do you see that if I multiply both sides by the red reciprocal 13/5? Oh, that's giving me 1. Now, wait a minute. What does that 1 stand for? Well, I just want to remind you that in calculus, we're always in radians. So that would be 1 radian, and it's per minute, no, per second. That's what that stands for, okay? So hopefully you're all right with that. Remember, you may want to watch this video or parts of this video multiple times in order for it to sink in. There's no harm in that, especially if you feel like I'm talking quickly and you need to rewind and re-listen. All right, so on number 5, a man that's 6 feet tall walks toward a street lamp which is 16 feet tall. All right, let me say again, the 6 feet and the 16 feet are permanent measurements. So the man's height and the street lamp's height will not change as time passes, which means those values can go in the original equations. So at a rate of 5 feet per second, now wait a minute, I got to figure out what is the 5 feet per second, because that's definitely a rate. So a man, let's see, he walks toward the street lamp. So my guy is, sorry, and my picture is facing the wrong way. So we'll say he backs up toward the street lamp. But anyway, that the distance from the man to the street lamp is x. So the 5 feet per second must be the change in the man's position. So the change in x over time. All right. And I'm going to put in a negative because x is shrinking or the man's moving to the left instead of the right. So I think that rate's going to be negative, just FYI. Okay, so at what rate is the length of his shadow changing? Okay, so at what rate is the length of his shadow changing? That's my question. The length of the shadow is S, and I don't know if you can see the guy's shadow kind of projected on the horizontal ground right there, but we want ds dt in this first question anyway. And it says when he is 10 feet from the lamp. All right, so that 10 feet is my time-specific value. So I've got a time-specific value of x equals 10 feet from the lamp. No, this is an interesting question because when you start to work it out, it's easier than you may think it's going to be. I'm not going to deal with the second question. That's like a part B. So right now I'm on a part A. So I need some sort of an equation where I have x's and s's, but if you look at my picture, I do not want capital T. Capital T's in the picture, but I don't want it in this equation because I just want dx dt, ds dt. I don't want any d capital T dt's in the picture. So I'm looking at the picture thinking about similar triangles. And I've got an inside similar triangle and a big outside similar triangle. And I can see if I compare left side to left side, I've got 6 to 16 as my scale factor. That's cool. Now, this is x, this is s. So instead of doing a t, let's do an x plus s. And that way I don't have any need for a third variable. Now, here's what I know. That 6 is to 16, so left is to left, as bottom of the little triangle is to bottom of the big triangle. Take a look, rewind it if you need to hear what I said. So I have to look at left side of little triangle to left side of big triangle, and bottom of little triangle to bottom of big triangle. So if I say, well, let me cross multiply and clean this up a little bit, I'm going to have 16s equals 6x plus 6s. Well, I can clean that up even further, and I can get 10s equals 6x. And if I want to, I can clean that up even further and say that s equals 6 over 10 or 3 over 5x. Because if I wanted an equation that has an s and an x in it, so when I do derivatives, I get a dx dt and a ds dt, I've got it. So I'm simplifying, making my equation as derivative ready as possible before I do derivatives. So from here, I'm going to say that ds dt, because I'm beginning my derivatives, equals 3/5, the derivative of 3/5 x is just 3/5, times dx dt. I'm going to start plugging in. So ds dt is what I wanted. 3/5 is just in the problem, so I'm not going to color code. dx dt I had, so I'm going to plug in -5. So that's giving me that ds dt is -3. The length of the shadow would also be measured in feet, so the rate's feet per seconds. So that tells me that as the guy walks toward the street lamp, that his shadow must be decreasing in length at a rate of 3 feet per second. And notice that my time-specific 10 feet from the lamp, it didn't matter. There was no place to ever plug it in. So that's kind of interesting. So now I'm going to go to part 2 of the question, which says, at what rate is the tip of the shadow moving? Now, the tip of the shadow would be measured by capital T. So now I'm trying to figure out a dt problem. All right? So this time, because I have dx dt, and I want dt, I would like my original equation to have x's and t's, but no s's. You might be able to structure something with s and t, since you actually do know ds dt at this point, but I would say just go back and treat this as a brand new problem. So this time consider that when I'm labeling my picture, I'm still going to use 6 and 16. I'm still going to say that this is x, all of this is t, but I don't want a little s because I don't want 3 variables in my problem if I can help it. So why don't I call that t minus x, and that gets around me needing an s. So I'm going to do the same thing. Left side of little to left side of big equals bottom of little to bottom of big. So now my equation has only t's and x's, no s's. I'm going to cross multiply the same way and say 16t minus 16x equals 6t. No, not pi, but t. So 16t minus 6t is 10t. I'm going to move the 16x over. T equals 16 over 10, divide by 2. Divide by 2 is 8 over 5x. So I'm making the equation as simple as I can before I take derivative. The derivative of a capital T with respect to little t equals the derivative of the 8/5 x, which is 8/5, times the derivative of x with respect to little t. I want dt, so I'm just going to go ahead and plug that in, nothing fancy. 8/5 is 8/5, nothing to color code there. Dx dt is -5. So my result is that the tip of the shadow must be moving inward at a rate of 8 feet per second. I don't say at a rate of -8 feet per second, because the negative is what tells me that the tip of the shadow is moving inward or it's shrinking in length. So -8 feet per second. So again, the red time-specific information, x equals 10 feet, it didn't have anything to do with this whole problem. All right, one last problem on this video portion. So a boat is pulled into a dock by means of a winch, which is 12 feet above the deck of the boat. Now that means my yellow piece, and I don't know if I can color in yellow and you actually be able to read it, but that would be 12 right there, and that is a right angle, so I'll mark that. The winch is 12 feet above the deck of the boat. So the winch pulls in rope at a rate of 4 feet per second. All right, so guys, this is the length of the rope, and it looks like that the rope is shrinking at a rate of 4 feet per second. So the 4 feet per second then is my dr dt. The length of rope that's connecting from that winch to the point of connection on the boat, that length of rope is shrinking. So I'm going to say that's -4 feet per second. Determine the speed of the boat when there is 13 feet of rope out. Okay, now determine the speed of the boat. Okay, so the orange piece we'll call X, and that measures the boat's distance from the pier or the dock. Would be a better way to say that. So the speed of the boat is the rate at which X is shrinking, the rate at which the horizontal distance from the boat to the dock is shrinking. So I'm being asked, what is dx dt? And when it says when there is 13 feet of rope, the time-specific measurement then is when there's 13 feet of rope, means when R is 13. And the latter problem, the 13, was constant. It's not constant in this problem because the rope will shorten over time, and the distance the boat is, X, will shorten over time. The one thing that doesn't change is how high the winch is vertically above the deck of the boat. So that 12 will not change over time. That's fixed. So that means 12 can go into the equation initially. So what happens to the speed of the boat as it gets closer to the dock? Okay, that question I'll deal with later. Okay, so I'm looking at it, and I hope you're seeing that the equation that will put an R and an X in the same equation, the most simply, is just use the Pythagorean theorem. So I'm just going to say 12 squared, and again, I can put 12 in from the get-go because 12 does not change as time passes. This is going to be relatively easy, so go ahead and do derivatives. So the derivative of the 12 squared is 0. The derivative of the x squared is 2x dx dt. The derivative of r squared is 2r dr dt. And guys, I did not do this in the last problem, but you're allowed to divide the 2 out so your numbers are easier to deal with. So I could go ahead and say x dx dt equals r dr dt. I can do that so my numbers stay smaller. All right, so let's plug in what we can. Right now, at that point in time when the rope is 13 feet, let me figure out what's happening with x. So remember, 12 stays 12. At the point where there's 13 feet of rope, then what I figure is the boat must be 5, 12, 13, 5 feet from the dock. So I can plug 5 in for x and 13 in for r. Now, I want dx dt, so I'm going to color code that in orange so it matches the way I originally labeled. Dr dt, I can go ahead and plug in as -4. So it looks like when I solve dx dt, 13 times 4 is -52, all over 5. So it looks like the rate at which the boat approaches the dock is -52/5. If you divide that on a calculator, I'm getting about -10.4. And the reason I'm going to decimals is because the next part I'm going to have to go to decimals, okay? So -10.4, and isn't it feet per second? Yes, because dr dt is in feet per second. So the speed of the boat as it approaches the dock is 10.4 feet per second. It's negative because that x is shrinking, but I probably wouldn't say speed's negative because speed's always positive, right? So what happens to the speed of the boat as it gets closer to the dock? Okay, in order to do this, as it gets closer to the dock, I need to shorten x or shorten r in order to actually make a comparison, okay? So I'm going to say, let's go to blue, and I'll say time-specific number 2. Because I cannot make a comparison if I don't have numbers to compare. Now 12 stays 12. What if I said when the boat's closer to the dock? So maybe when the boat is 3 feet, we'll say, from the dock instead of 5 feet from the dock. So what happens when it's a little closer? Well, at that time, I know that the rope would be a total of 12 squared plus 3 squared. So the rope at that point would be what, 144, 154, 153 feet long at that point. So a little shorter than 13. Okay. Now we're going to do the exact same thing where we had right here that dx dt. How about I go ahead and say it's r over x, the r dt? And let's start plugging in measurements, and then we'll use our calculator, okay? So I want dx dt. I want to know how fast is the boat going now. The r at this point is the square root of 153, which I just calculated. The x is 3. I just made up any value where x was shorter than 5. You could have done it for anything. X could have been 4, or you could have made it 1 or 2.5, whatever you wanted x to be, by the way. Dr dt, I know, is -4. So now if I've actually got right now, I've got the exact measurement. But what I want to do is actually plug this value into my calculator so I can compare decimals to decimals. So let's see here, 4, I'm doing this on my calculator, times the square root of 153. And then divided by 3. I'm getting that this value is -16.4924. Remember, I need 3 or 4 decimal places to satisfy the AP. So that's going to be feet per second. So wow, what I realize now is that as the boat gets closer to the dock, it's actually moving faster. Its speed increased from 10 to 16 feet per second. So why we need bumpers there so the boat doesn't crash into the dock, right? That we protect the boat. So guys, at this point, we're not obviously going to be able to do group work necessarily like I'd like to do. We're not going to work on A24, which is the circuit training worksheet, yet. Remember, what I want you to do is start with the Albert assignment, and it's got some review of curve sketching, which is good for you, especially if you're going to take the AP exam. But I want you to do the Albert assignment first because you can get feedback on what you're doing. Then we'll work on the worksheet, the circuit training worksheet, and I'll be setting up online office hours. I think probably using the Canvas conference feature. I will post an announcement on Canvas to let you know more about that. But that way I can maybe work some problems with you as you ask questions. All right. Thanks, guys.